So we're going to continue moving forward, and we're going to talk about two comparison tests. We're going to talk about a direct comparison test and also a limit comparison test. So far, we have talked about lots of different sequence and series. We've talked about the fact that geometric and p-series, those both converge. And then, we have like a harmonic series, which is divergent. And so what we're starting to notice is we have a couple of benchmark series that we just know and understand, and we hold them in a high esteem, and we can use them to figure the divergence or convergence of other series out. And so this new way we're going to talk about is by comparing a new series to a series that we already know. So the first comparison test we're going to talk about is the direct comparison test. So the direct comparison test says, hey, let's consider some series of A as well as some series of B. These are both two series. They're both positive, and A is going to be smaller than B. Okay, so all of those terms in A are going to be consistently less than the same nth term in the B series. And so what we can say, we've got two situations, and this, I'm not going to prove it for you because I think it makes pretty good sense, but if our sum for B converges, then our sum for A would also converge. And remember, A is smaller. So if we think about this, part one, so a convergent series, if we were illustrating it, might do something like this, right? So if that sum of B converges, then if A is less than it, it's also going to have to converge. And then similarly for the second part there, if A diverges, so the smaller one diverges and goes off here to infinity, and we know that B is above it everywhere, then B would also have to diverge. Okay? So that's what the direct comparison test says. So what we're going to do here is we're going to show that this sum, the series 5 over 5n minus 1, is divergent. Okay? And if we want to show that it's divergent using the comparison test, I'll have to show then that there's a series where all of the terms are smaller than it that also diverges. Okay, so we want to find a series that the same nth term would be less than this nth term. And if we know that that smaller series is divergent, then the series that we're given here, 5 over 5n minus 1, would also be divergent. So let's think about that term, 5 over 5n minus 1. And I can rearrange this a little bit because I can divide everything by 5, and that would give me 1 over n minus 1/5. Okay? So what we start to notice here is that this looks like a series we're familiar with. 1 over n is our harmonic series. And we know that a harmonic series is divergent. So if we think about this, we know that 1 over n minus 1/5 is always going to be bigger than that harmonic series 1 over n. And if you think about our denominator here, n minus 1/5 is smaller than n, right? So n minus 1/5 is always going to be a smaller value than n. So the smaller your denominator, the larger your fraction, right? 1 over 2 is bigger than 1 over 3. 1 over 5 is bigger than 1 over 10. So the smaller the denominator, the larger that actual fraction. So in this case, the nth term of the divergent harmonic series 1 over n is always less. It's always going to be smaller than the nth term of 5 over 5n minus 1. So the smaller series is divergent, then the larger series must also be divergent. So we're going to do another example here. We are going to show a convergent series. So we're going to show that this series from 0 to the infinite term, notice my index starts at 0 here, of 1 over n factorial. We want to show that it converges, and we're going to do this by using the comparison test. So something else that we do when we are trying to analyze what is occurring here is we might list the terms just to see what the series looks like and see if it looks like something that we are familiar with. So if I list my terms here, if I start adding this up, I've got 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, 1 over 3 factorial, right? We can do this all day. So if we look at what that is, 0 factorial we know is 1, so that is 1, plus 1, 2 factorial is 2, 1/2. 3 factorial is 6, 3 times 2 times 1, so I've got 1/6, and 4 factorial is 24. So this is what our series looks like. And we want to ask ourselves, does this look like a previous series? Okay, so that's what we're always thinking about. Have I seen anything else that looks like this? And we did. We could say, well, n equals, this is very similar as n equals 0 to infinity of 1 over 2 to the n. And, remember, we can always re-index these and make them look different. N equals 1, this would be the same as n equals 1 to infinity of 1 over 2 to the n minus 1, right? So just changing that index changes the exponent there. And we did an example in one of my previous videos that looks like this. And this was a convergent geometric series. We did that previously. And the terms for this, what might our terms here look like? We would have 1 plus 1/2 plus 1/3 plus 1/4. So they're all smaller except for those first two. And the way we can handle this is by coming over here and I can say, all right, well, in this case, the original series we started with, n equals 0 to infinity of 1 over n factorial. Those terms are all less than, well, I can say 1 plus this new series, n equals 0 to infinity of 1 over 2 to the n. And since the right side here is always a convergent series plus 1, right? Since this is convergent, then on the left, the series which is smaller must also converge.